What a segue. I mean, I hardly ever have the chance to be talking after people that are so passionate about absolute track geometry and track geometry. So this is kind of a good start for me to, I will focus, I will also talk about absolute track geometry, but obviously it's going to be from a different perspective, and I think it will be useful for everyone to have a kind of see how we understand that, and it's quite exciting to see how you implement it in works. So, okay, here we go. So our presentation is as followed. We will be talking about the EM-SAT that you already mentioned but didn't use. That's interesting. The history, what is the EM-SAT? The history of the EM120VT, virtual track. The evolution of track geometry. Then I'll introduce some case studies of the new technologies that we implemented. There will be renew old nudes, automate turnout inspection, and advanced sensor fusion. And then Mark's going to take over for the machine part, where we talk about the new machines that we have rolling out, the EM100 VT2 and the EM100 VT3 that is coming to the UK. So let's start off. This is the EM100 that we saw on the previous slide. I think that's probably the same machine. So what does this machine do? It basically has a satellite which anchors to a fixed point or a spigot. That's the right term that I say, to a spigot. And the satellite goes to the spigot, locates the spigot, and opens up a laser beam, a cord to the machine. And as the machine drives towards the satellite, it measures the track geometry and calculates the values to which the track should be aligned. So out of this process, you get the lifting and the alignment for the track machine. But however, the machines weren't quite as successful because they just work with 2.5 kilometers an hour. So the idea didn't quite catch on as we would like. And this is most likely because hand trolleys evolved faster and they measure with the same speed, so it's more convenient to have a trolley to push around. So what we ended up is, so maybe a little jump out what my position within the company is. I work for the Department for Technology and Innovation, and my job with my colleagues is to figure out how we put new technologies into machines and how we can make the interfaces between our machines more seamless and more effortless, that there is less errors and is more efficient. So in 2018, we had this idea, maybe we buy one of the EM100 VTs back and repurpose it for our use. So we bought this from ÖBB, the machine that had a quite bad accident, and we refitted it because we needed a platform to test the new technologies, to test new sensor systems, to test new softwares, and to test new processes. So in 2018, we presented this machine on InnoTrans, and this is the setup of the machine. You have GNSS, inertial measurement system, and all the tech that at that point we had available. We equipped the machine and just tried out how can we improve on the status quo without the need to have a daily operation running. Just see what can we squeeze out of a measuring vehicle. And this is how we came up with the fixed point measuring system. And this is kind of the evolution. In the 1950s, you measured the spigots and you had kind of a speed of 0.4 kilometers an hour. With the EM-SAT, you came to the 2.5 kilometers an hour. And right now we made the jump to 80 and 100 kilometers an hour. And I think we will be able to deliver the system on platforms that go 180, maybe 200 kilometers an hour. So this is quite substantial, and I think competitive with hand-pulled trolleys. So what does the absolute track geometry does? Let's start. I also like to explain or try to from people that are not from the industry what is actually relative track geometry. Because the vehicle starts with relative track geometry that is an inertia-based navigation system. And what it does, it gives us a space curve. So it tells us if the track is one line. And basically what we're looking for is our defects within our space curve. Those defects cause derailments. And if you're not going too fast, this is all you need to run safe trains if you're in a free space. Because as you can see, the space curve might have slight errors that add each up. And if you have free space, it doesn't matter, the train will pass safely. But once you you have kind of constraints with obstacles, this is where you need to pinpoint the trajectory within space and confine it and compensate for the errors that you can pass, for example, on a bridge safely or don't have any other problems. So to make these constraints, we implemented a stereographic image system. And it is positioned at the side of the vehicle and looks at the masts and measures the distance to the spigots or the targets that we implemented. And also, because there are cameras, it's quite easy to read QR codes and have identifiers for what you're measuring. So since we are before lunch and it was quite a long session, I want to do a little exercise with you all together. That's the exercise. We're going to try to estimate the distance. So each one of you will try to estimate the distance. What is the distance from you to this marker? So first of all, I want everyone to stand up, please. Okay, perfect. So I need your thumbs. I need your right thumb. And try to aim at the target so it aligns at the side of it. And then take your left arm and close your left eye. And then jump with your left eye to the other eye, and then you will see that your thumb will jump depending on which eye you're looking through. You need to have a straight arm. And then you count how many trains are between those jumps. So I will measure how the distance of one train, and then you need to see how many trains are that. You calculate, you multiply it by 7 or 14, depending on your height and how far your eyes are apart, and then you can estimate what is the distance from your perspective to the board. Let me get a. So a train is around 10 centimeters. Can you do the math? Does it work out for you? Some confused faces? No, those guys are experts. They get it. Okay, thank you very much for the audience. So if it didn't work for you, we have lunch afterwards. We can try it afterwards, also talk to the experts. But this is the basic idea. You look through 2 different camera lenses and see how the perspective changes. You have this technology deployed on Mars through NASA, so it's quite well known, and you can use it while hiking to estimate how far how far it is for the next hill. So right now I will pass through those markers so you have an idea what they look like and how they feel. Obviously, the design can be changed, but this is what we came up with. So we come to the case studies, what this particular technology enabled us. And the case study is renew old routes. Obviously, going from an old one to a refurbished route that was and we did a digital survey at the Deutsche Bahn. That was the rehabilitation of the speed line SFS 1733, basically going from Kassel to Würzburg. It was in operation since 1991. Top speed is 280 kilometers an hour. It's a double track, 60 tons per day. It's about 180 kilometers of route length. We have 88 kilometers tunnels and numerous bridges. So the challenge was this route needed to be renewed, upgraded, and the renewal was planned for 2013, the first 2020 and 2023, so it's underway, the renewal right now. And the challenge was, well, a conventional survey of the track that was required by Deutsche Bahn regulation would require a close down of 100 days. And within those 100 days, you would have a clipboard and a crew, and you just walk the line and pick up all the obstacles and objects that are relevant for your renewal. And I think it's a very nice exercise for you personally, but closing down the line for 100 days is not quite feasible, especially if it's a high-speed line that is in high demand and needs to be renewed after just 30 years of operation. So that was quite a bad option. So we teamed up with a civil engineering company to do the survey with our test vehicle, and we kind of equipped it with an oversized rig. It reminds me a little bit of the Sentinel from Matrix. But let's focus on the tracks. We could do it just in 2 night shifts. We would run the track with the absolute track geometry and align all this data. And so this is how we aligned the data internally to have all the cameras and the sensor systems. We put out a test field in our yard to calibrate all the systems together so they're perfectly matched. Down here you have the setup that we use at that time. So it's our research vehicle that changes all the time. We put new systems on and off. One interesting thing is the georadar, ground penetrating radar, that we also use to detect objects within the track. And these are some impressions from the ride. This is the ground penetrating radar, the fixed point measuring system. And after the 2 night shifts, this is how the inspections look like. Because the regulation is quite specific how it should be performed. We did virtual offline track inspections. And the track inspection was basically we had all the people that would be on track in our room, and they took notes as we were progressing through the track and took notice. And in the beginning, it was quite slow because you need to adapt to the new environment, because it's easier to pick points if they're real, and it's difficult. It takes time to adapt to something virtual. But after 2 days of adjustment, we were rushing through all the track, and it was quite convenient process. And all the data was captured with Provi, the design software solution from Obermeyer. And the end results were kind of conventional paperwork that is to make the process seamless. So all the data was put into the platform, but the output were plans, and they were printed in paper form. So this is kind of the discussions we had about obsolescence and if data formats are readable in 20 and so forth years. And as you can imagine, 1991 isn't as far back as most of us wish it is. But data from that point was scarce, and even the company did the planning for this site. And they had to go through the archives and see if they had the data on site. And basically what they recovered were just printouts. And this is the nice thing about paper. It doesn't degrade as fast and doesn't develop as fast as the IT technology right now. So this is the approach that we chose at that point, and also to mitigate the risk of interferences with further down the line processes. So the next case study is turnout inspection. I mean, that's a point I don't need to reiterate, but just some numbers. 90% of all network-related delay minutes are caused by turnouts and crossings. Thomas Böhm from Konux did the analysis. So turnouts and crossings are kind of very critical part of the infrastructure. And today we manage them most of the time with manual inspection. And there are quite a number of measurements that you need to perform on track. And we came up with a number around 20 minutes that you need for a turnout inspection. Maybe, do you think it's more? What's your experience? So who says it's more? That just raise your arm than 20 minutes. Quite a few who think it's less. Okay, so let's go for the more. There is a majority. So it's a quite dense number, and it's stressful. So as you maybe you know, we partnered up with DMA, the measuring company from Italy, and they developed the turnout inspection system. And with the progressing technology, you see that more and more bandwidth is available for our applications. And with a sample rate of 1,000 hertz, you can measure rail profile at a speed of 30 kilometers with every 10 millimeters, or maybe every 20 millimeters when you go 60 kilometers an hour. But this will increase, obviously, in the future. And once you have this type of resolution, you can build systems that can do your turnout inspections because you have enough data and you can pick the right spot where you need to do the measurements. And this is what they did with TraxNet and the measuring system. So this is an output of the turnout inspection from their system. This is the software that accompanies the software system. So for each turnout, you put in what kind of turnouts you have, and then you adjust the parameters that you need to your specific needs. And those are also case studies. So we have, there are not all systems that were deployed, but this is the concrete numbers that I have right now. At Infrabel, there are 2 systems in operations with 60 kilometers an hour. Eurorail Scout has 5 systems in operations. And it's interesting because they are pulled and pushed. So this is a vehicle that you can snap in front of a logo and pull it or push it, which is quite nice if you're in a train station where you need to reroute. And we are also happy to provide JR East. They bought 1 system, and now they extended the contract to purchase further 4 systems, which makes us quite happy that they like this technology. And the case study and the business case around it, you can measure up to 200 turnouts in 6 hours. At Amsterdam Station, that was what we recorded. So calculating 200 turnouts with 20 meters, that goes up to 66.7 hours that you would need to just measure. So it's 6 hours of time that you gain, that you don't need to close down the track, that you don't need to endanger or put people into a dangerous position. And it's fully automated and creates the reports. And it makes them reproducible. But there's a huge caveat to that. You're measuring under load. And this is quite a controversial issue. And you could either take the argument, well, you shouldn't measure under load because our regulations, I don't know how it is in the UK, but our regulations is set up to measure without load because it is reproducible. If you don't load it, it's quite easily reproducible. But once you load it, you have to, the measurement isn't as reproducible because you have to apply the same amount of load. So this is what we observed with our customers, that they are quite different perceived. And there are some statistics behind it. I hope you can read it. Maybe in the handouts you can see what are the average deviation from a sample of measurements that we did. Another statistic which I think is more interesting is kind of to give you an overview how big is the spectrum of deviation that you expect. And imagine that if you have a regulation that requires you to measure unloaded and suddenly you put in a system that measures loaded, you will spike in defects that you're creating, and obviously you will create stress on the organization because you have to suddenly get rid of all of them. So I think those are interesting discussions within the infrastructure providers and the regulators that you need to have the discussions. What are we trying to achieve with our turnout inspections? Is it just sending people to the field, or are we trying to reduce risk of derailment, and what are our safety margins? So this is an outlook into what we are working currently on. It's not the only thing that we're working on, but just to give you an idea where we spread out, and it's not ready yet. So it's still a rocket in the hangar that is being built on, and it's advanced sensor fusion. We partnered up with a company that makes unmanned aircraft systems. And the thing is, LiDAR and point clouds are becoming a thing. So more and more data is available. So there's a trend, like we see it in the previous presentations. There's more data coming. But how do you utilize it? There are numerous of presentations showing point clouds. So I will add another one to this. But this one is how we combine different measurements. So on the top side, you see the measurement of the point cloud from the measuring vehicle. And on the bottom side, this is the LiDAR system that was deployed on an unmanned aerial system, so basically a drone. And what we're trying to achieve with that is to come up with use cases how we as track engineers can utilize those data. There is no use in producing data which is not utilized. So I give you an insight into a demo how we do with object recognition. So this is a short walk through our point cloud that detects objects and marks the platform edges, the catenary, and then further down you can see how you can really measure points between objects and not just the clouds. So this is how a railway engineer would use a point cloud. You always go into track and see if everything is aligned. What are your obstacles? This is another interesting screenshot where we combined two data. So one was measured with the drone, the other one with the measuring vehicle, and there were obviously different temperatures. So what you see, I would like to point out, in the catenary, in the lines, that you have different sags because of the temperature difference. So that was kind of something that caught my eye that could be interesting for maintenance activities, or just to have this perspective. And other use cases for the drones are just the visual planning aspect. If you need to change your route, how do you need to go out in the field, or you can do a preliminary planning of your working site, or maybe do inventory and check what kind of assets do you have deployed, because over time tracks change and it's not always the way you have designed it, because over time some cables might have creeped in and some underpasses were built that were not documented as well. Condition, obviously, and one strong use case is incidents. What happens if an accident happened? How do you get an overview just in real time? So that's enough for the soft part. I would hand over to Mark, who will talk about more about the yellow machines.
Right. I'm the person standing between you and lunch. So the pictures, and most of this is pictures, are obviously all available for later on. So if we rush through them, or anybody wants to talk about them later, the pictures are most easily available. Briefly, what I wanted to talk to was how do we move on to the next generation. The VT2 machine was displayed at the Munster exhibition in May of last year, How did we get there, and ultimately where are we going for making this for the UK? So early stages, back to the same idea. How do we repurpose a vehicle? How do we go from the first one where we just put some not simple systems but research systems onto the machine? How do we try to make that machine actually really useful in the future with as much possible equipment as we can get on it? And you can see the early concepts. When we come to the UK one, it's going to look very similar, in fact, as we get there. There's moving into a slightly more digital age, a kind of plan view. How do we fit everything on? What kind of things could we do? You can see the 3D scanner mobile mapping on the front is looking a little less alien than the version we started with in the beginning. We need to monitor the vehicle body movements. We're going to do ground penetration radar, and we now have 2 different versions of ground penetrating radar. As we mentioned, measuring the absolute and relative track geometry, both loaded and unloaded. We have some devices for being able to recognize the rolling marks in the rail itself as you're moving along, and the usual what in the UK is plain line pattern recognition, video monitoring. We can also put some driver's view video. If you're going to be going up and down the track, you can always benefit from video recording of the track that you're going through and tying it all in eventually to catenary wire position. Very quick run through the different elements. One of the key bits about all this is tying all these measurements together. So it's no value, I mean, there's always value in just doing the measurements. It's very useful to know your ground penetrating radar scan of what's underneath the track. It's useful to know your geometry. It's useful to know your overhead wire. It's actually a lot more useful to have all of those things tied together to a single location, absolutely together. And in the long term, you want to be able to understand what's happening. If you have ground penetrating radar that tells you about what's going on in your ballast or your formation underneath, and you have over time history measured geometry data, you start to be able to determine effects that come from what's happening underneath the track in the first place. Yeah, we had to try and fit all that on and in, so we took a layout that was looking like this when it got back. You'd be surprised, but that's a lot more organized and clean than the version we got back for the UK. We designed a CAD layout for hardwood fit, and we got on to actually taking the machine apart. We realized we need to make more space up front for the people sitting. We need more space for computers compared to the old one in extreme more. We need power supplies and uninterruptible power supplies, battery to keep it all up. So here's the framework then being set up inside the machine to be able to create that extra seating area, to create the space for the server room that we need inside there. The same thing with the rear cab for the machine, new design layout for the rear cab as well. And we realized in the old version of the machine, they had the space and they didn't have too much that they needed to do. So we had to rewire it to make sure we could gain a lot more space. A bit dark of those pictures, but there are the rewired cabinets giving us the space. Putting all this in, suddenly you realize we need an awful lot more power than we ever needed before. Driving all these measurement systems and all the computers and processing that you need to manage it, we need new power, so we had to be able to fit a modern generator to power all that into the engine room. Provide cleaner power is also another key element of it. We already talked about the stereoscopic camera, 2 cameras picking up the same marker point and using the relative offsets that they've got to give you the exact position of your piece of track relative to that. Using light-based system, Christoph already talked about loaded and unloaded. Relative track geometry, the space curve used by the measuring frame. In fact, later we're going to use just simply the bogie of the machine as the measuring frame to give you that space curve with an IMU on it. And in the meantime, Plasser and Toro Group has acquired DMA, so they're now part of our internal group, providing, developing and actually building these measurement systems on their own. We've put a lot of effort into the ground penetrating radar. We're working on artificial intelligence for analyzing these ground penetrating radargrams. And you can see some trials we did where we put an old bomb into the track and then used the ground penetrating radar to detect where it was and what's there. The Regal system, the VMX for producing, as I said, it now looks a little less alien than it was before. Examples of the plane line pattern recognition. Out of that, those line scan cameras, you can actually recognize and detect with AI information about the rail that's actually installed in the track that you've got. And to do all this, we have a company within the Plasser and Tora group that ties all of this together. And one of the absolute key bits behind it is being able to display the data to the end customer in a way that they can really analyze, understand, and merge together, as I said, as one of the key critical things that we're trying to achieve. And it's that accurate localization of all the individual pieces and tying it into your grids, your survey controls that are actually there, and then displaying it back in ways that people are used to seeing that they can make sense with. So very briefly, the EMSAT, another point of digitization. Richard, your name is emblazoned in virtual. So as part of what we're doing, we also laser scanned the vehicle and created a point cloud of the vehicle itself so that we can work out how we're going to fit everything in. There's an example for the UK, and I appreciate we're now out of time, but it gives you an idea of what we plan to fit onto the UK vehicle itself. As the setup, and using the point cloud, you're able to take the roof off the vehicle and work out where you're going to put things inside. We can look at the vehicle from underneath. You can take it from any angle, and when a designer comes back asking for something, we can take a quick measurement. Yes, we can fit that there, or no, we can't. Vehicle is now in our workshops in West Ealing. As you probably can't see because the picture, at least from here, is a bit dark, but we've removed the engine, removed the gearbox. They're away for overhaul. We've taken an awful lot of cabling out. The old satellite is gone. All the trolleys underneath are gone. So we've cleared out, the interior is now cleared out. We've cleared all the space, ready to start preparing for installing all of those same measurement sensors and equipment that we were showing on the VT2. So very, very quick run through, but it's all available there, and the bulk of it is pictures just to show you where we are right now. With those EMSATs that you started on right in the beginning, giving them a new purpose in life. Thanks very much.